Welcome back. I'm now going to return to the risks board we introduced in episode 1 to see how we are progressing with the risks that you have to consider and mitigate for when running digital services. We talked about some of the ways that AWS designs and operates its data centers. We spoke about some of the access controls, if you remember, and we also introduced the AWS Nitro system to help mitigate some of the risks from bad actors. And also, the AWS network is segmented to reduce the risk of lateral movement to help protect against malware as well. In episode 5, we spoke to Elaine Harvey, who explained how the AWS service teams operate. We learnt from her how the teams mitigate the risks from introduction of bugs, and also how we very carefully deploy software to reduce the risk of change or deployments. But you'll notice there's still a couple of software risks left on the board. First, we'll cover surges in traffic. It's useful to ask, why exactly is this a problem? What happens when a surge of traffic hits your service? Imagine you're operating an application that supports citizens paying their taxes, and it's the deadline for annual payments. So what we're going to do is plot a graph showing the response time, which is the time it takes the service to respond to someone trying to pay their taxes, and we'll plot that against throughput, which is the number of transactions per second that are arriving at the service. So you can see what happens as that rises. So we're plotting throughput against response time. What you'll see is that as the throughput starts to rise, the response time will start to rise, but very slowly. But eventually, your service will reach this point where it gets very, very busy and the response time starts to rise very rapidly. Now, what happens if you're a client of this service? If you've architected correctly, you will set a value called a timeout. So what happens with that is the client isn't just going to sit around waiting forever for the service to respond. It'll wait for the timeout and then it'll go away. And unfortunately, if the service responds after the timeout, then as far as the client's concerned, that service is no longer operating at all. What makes matters worse is the client will probably then retry and come back again with another request, which adds to the amount of traffic hitting your service. And if you've ever been in this scenario where you have a service you're operating and there's too much traffic, it can be very difficult to rectify. Now, we call this scenario overload. Now, imagine your service for allowing citizens to pay taxes was working correctly up to this point. And let's say this was 5,000 transactions per second. So at that point, it's still operating correctly. Then let's say the traffic rose to 6,000 transactions per second. And at this point, you've experienced overload. What you'd like to do is to keep the service operating as long as possible. To prepare for this scenario properly, what you would do is performance test your application in advance and make sure that you'd adequately scaled your service and also introduce some automation to add more capacity if needed. But let's just say you've hit a really unexpected surge of traffic. It would be much better to preserve the work that you were doing at 5,000 transactions per second than have the service stop completely when it gets to 6,000 transactions per second. One technique we use in AWS to protect against this situation is called load shedding. In one sense, it is simple as it sounds. When you reach the point where you can no longer accept more work, turn the excess work away instead of accepting it, so you can keep the service running. It can be hard to visualize the effect of this, so I'm going to draw a new graph. So if throughput is the number of requests sent to the server, then we use the term goodput to mean the subset of this which are handled correctly and get back to the end user in time to be useful. The overload scenario can be seen here by plotting goodput against throughput. As the traffic at the server starts to rise and throughput increases, then for a time, goodput also increases, so the server is handling all the requests that are coming in. But what happens as we reach the point of contention, the goodput starts to tail off and then it will drop very rapidly. So this is the overload situation that we want to avoid. So if we redraw this using the load shedding technique, what we do at this point here is to start turning away the excess traffic. So we will maintain goodput at its current level. And we'll do this for as long as possible. Now note, this is not a complete solution to the problem because eventually the cost of turning away all that traffic will also consume the service as well. And so the goodput will eventually drop. But if you see what we've managed to achieve here, we've bought ourselves valuable extra time in which we can use to solve the problem by adding more capacity or changing the configuration of the service. So this is just one technique that we use in AWS to handle the situation of overload. I've been talking about unexpected waves of legitimate traffic that are hitting your service, but there can be unfriendly surges, usually in the form of distributed denial of service or DDoS attacks. This is when an attacker floods your service with internet traffic to prevent users from accessing connected online services and sites, or even cause it to crash. Fortunately, the AWS Shield, which is a service that automatically detects and mitigates sophisticated network-level attacks, is provided for no extra charge whenever you're using AWS, and that works by filtering out that illegitimate traffic. If you need higher levels of protection, you can subscribe to AWS Shield Advanced. Next up, we're looking at poison pills. If you recall from episode 1, a poison pill is the name we give to the situation where a single client can impact a service by poisoning each instance of the service one at a time by sending an erroneous request that makes them crash and retrying again and again until all of the instances fall over. I'm going to describe two techniques we use at AWS, particularly in services where availability is absolutely key, like Route 53, which is the AWS Domain Name System service for routing customers to digital services on the internet. Remember we spoke about the example of using a payments application. Let's say you've deployed your payments application to 8 servers, like this. Now imagine you have a bunch of different customers using these servers, A through H. All the customers are sending requests to each of the servers at random. So let's say customer B sends a request here, D sends a request here, G here. Now, let's say customer A sends one of these malformed requests and they send it to this server here, which causes it to crash. What happens is customer A will retry with this server. It'll make that crash as well. Then this one, and eventually customer A will retry and work their way through the whole fleet, and now the service is down. So the impact or failure radius here is equal to the number of customers. Now let's see if we can do better than that. One approach we take in AWS is to introduce further fault isolation by creating boundaries between smaller instances of the service, similar to how bulkheads are used on a ship to divide the hull into smaller failure units. We call these units cells, and this is an example of what we call cellular architecture. You can see here that I've spread our original 8 servers into 4 cells. The customers are now allocated to one of these cells only. So these are the cells. A and B are allocated to cell 1, C and D are allocated to cell 2. Now let's see what happens in the poison pill scenario. Customer A is added again with their malformed request. They send it here and it takes out this server. And then they retry and send it here, and now this server has also crashed. So the first cell is now unavailable. So customer B is unable to make a payment, but customers C through H are now unaffected. So we've improved things by quite a bit. The impact or failure radius here is equal to the number of customers divided by the number of cells. But we can do better. I'm going to show you a different way of tackling this problem. Here are our original 8 servers, but what I'm doing now is allocating customers to a pair of these servers at random. They're all shuffled up. Let's see how this changes things. So customer A is off again with their erroneous request, and they send it here, which takes out this server. And they're also allocated over here, so they send another request in and take out this server. So you can see that customers E and H have been initially impacted here, but they will retry. So customer E is also allocated to this server and are able to make a payment. And customer H is also allocated down here, so they're also able to make a payment. So now everyone is able to make a payment other than customer A. So we've managed to improve things quite a bit. So the impact or failure radius here is equal to the number of customers divided by the number of combinations. So we call this technique shuffle sharding. And this technique uses a little bit of math to greatly improve the resilience outcomes for customers, particularly in critical services like Route 53. The maths uses this formula, which you may remember from school. This formula has the nice property that as the number of servers increases, the number of combinations increases very rapidly indeed. So with just 100 servers and allocating each customer 5 different servers from that, the number of combinations grows to 75 million. And if you try to calculate the number of customers who would have the same 5 servers overlapping, then that is just 0.0000013%. That's magic. We use shuffle sharding across many of our services to keep our customer workloads resilient. So I've shown you just 2 of the many techniques that we apply inside AWS to mitigate some of the software risks we described: surges in traffic and poison pills. In the next episode, we're going to talk about some of the techniques, tools, and AWS services you can use to build and operate your own applications in a resilient way. See you there.